2017.
Hello everyone. So I will be brief. I will try to talk longer than 30 minutes. So who am I? I'm Guillaume or guedou. I'm French. I'm sure you can tell that from my voice. I don't do reverse for a living, but network security. And maybe you know a tool I maintain. It's called Scapy or Scapy in French. It's a tool used to play with network packets, send them, receive them, and also express them in a really easy way. As a disclaimer, I have to say also that I'm not a radar or MySM power user, so today I might say incorrect stuff, so please accept my apologies in advance. So this talk will be about r2m2, which is a plugin for radar. If you don't know radar, that's an open source reverse engineering tool with a nice command line interface. And MySM, that's a Python framework. I will give you later on example about MySM. So the goal of r2m2 is to ease reversing a new architecture by using MySM as an assembly or disassembly engine, and also using the symbolic execution feature of MySM. And the goal of this tool is also to bring R2 features to MySM, for example, the graphical interface, shortcuts and tools, and so on. And because I'm not, let's say, a reverse engineer, I want to keep all of the smart parts, the assembly logic, into MySM. So for me, for my project, r2m2 has at least 3 benefits. The first one is that it helped me to implement a new CPU architecture faster by relying on MySM, because it's highly expressive. It's kind of really convenient to express a new architecture. And also because MySM is written in Python, I was able to modify the implementation on the fly while reading the CPU architecture datasheet. Also, it gives you, or gave me at least, flexibility because I was not stuck with a single usage. So at the beginning, I chose to use MySM for this, let's say, weird CPU architecture. So it gave me assembly, disassembly, and emulation. And r2m2 is giving me the graphical interface of R2. So I'm not stuck with like only one tool. I can use both. And finally, r2m2 is translating the internal MySM expressions into radar Ether, which is a R2 internal expression. And here, the main benefit of r2m2 is to use dynamic analysis features to enhance static analysis. For example, to find out the address of a string, which is accessed by, let's say, a move. Okay, so r2m2 is available on GitHub. Sorry, I'm not drinking alcohol, just water. So r2m2, you can get it on GitHub. It works on Linux and OS X. It also works on Docker. You can pull an image on Docker Hub. I will recommend that you use and choose a Docker image, because some dependencies are kind of difficult to install. So please go for Docker. You can check it on my GitHub page. So why did I, at some point in my life, needed to call Python from C? Because indeed that's kind of weird. So in, let's say, 1 year ago, I discovered a new, or let's say, exotic CPU architecture, which was not implemented in any other tool. Excuse me. It's really warm here. So I started to play with the firmware update, so update binary, and I played with binwolf, strings, and these tools, and none of them managed to find the architecture. So a friend of mine helped me to desolder the SPI flash and dump it. So at the end, we got a bigger binary. So we tried again binwolf and strings and other tools, and we didn't find anything. And one morning, another friend came out with the following format string. If you have a close look, it could be something you will use in your software in order to dump register values. So of course, what we did next, we asked Google, and Google told us that it was a Toshiba MEP. So what I decided to do next was to implement this architecture, Toshiba MEP, into MySM. Sorry, no. There's something before. Like back then in 2015, this architecture was only implemented in binutils. So for example, that's an output of objdump, where we can see here that there is some vector table with jumps. And for example, here we have another function, like further away in the binary, playing with a stack pointer. And then I decided to implement it in my SM because it was not really useful to actually reverse the binary. So let's try the first demo. I hope it won't fail. So it's too small, I guess. Oops. Is it big enough? Yeah? Okay. So if you want to use r2m2, the first thing you need to define is a variable in order to tell him which architecture you want to use in R2. So it's r2m2 arch. In this case, that's MEP in Little Indian. Then you need to launch R2 and you specify the architecture. So usually the architecture in R2, you specify x86, ARM or MIPS. In this case, that's the name of the plugin. And then that's usual R2 stuff. You specify the binary. Then I can try to disassemble 10 instructions. That's, again, regular R2 commands. The only magical trick here is that behind R2m2 is calling Python code, is calling mySM in order to disassemble the architecture. And we can see that we have the same output as in objdump with the jumps, and then move 0, R0, which are knobs in MEP. I said before, R2m2 is able to translate between expression in mySM into R2 ASL expression. So we can check that. We can specify a variable with for R2. This one will enable a new display. So we can disassemble 10 instruction. And here we can see that mySM was able to provide the semantic of the instruction to R2. So we know that if we execute this instruction, this jump will jump to address 100. Something we can do also is type AA. It means analyze in R2, and then display the call graph. That's not nice. So screen color 0 should be black and white. So what you have here, that the call graph, that's exactly the same code as the one I showed in objdump, except that it's much nicer to use. We can go everywhere we need and see the blocks. Okay. So if we go back to the previous display, I said before, mySM is able to translate expressions, so we can also emulate in R2. So if I type AEIPC, R2 will initialize its virtual machine, initialize the internal PC, and we can try to step one instruction. So obviously, hopefully R2 will jump to address 100. That's what it did. We can disassemble five instructions. See, okay, sorry, color. Oops. Okay. Typo. I won't drink. Okay, so PD5. So PC is here at the correct address. And what I want to do next is do 2 more steps in order to have 40 or 0x28 into a register R9. So right now, R9 is equal to 0. Oops. Okay, 2 more steps. R9 is equal to 28, and we can check that PC moved to this instruction. So that's it for this first demo. We need to remember that everything is done dynamically by calling Python and converting internal mySM expression into R2. So for me, that was a nice way of improving what I had with objdump and start reversing the binary. So what I want to do in the next part of the talk, okay. Full screen, sorry. Okay. Well, in the next part of the talk, I want to introduce mySM and mySM features by giving you examples. I will also show you how you can implement your own R2 plugins, and finally, I will conclude with R2m2 designs. If you want, you can go to this website. I also just send a tweet, and you can get the links from the tweet. On this website, you will find the slides in HTML and PDF, and also a file in text file where you can just copy and paste all of the examples. And they all work in a Docker image of R2m2. So mySM is a quick tutorial. That's a Python-based reverse engineering framework with really a lot of cool features. You can assemble is assemble, of course. You can express instruction semantics in order to emulate. And also, and for me that's the most interesting feature, you can really implement a new architecture. On their website, on the blog, and on the GitHub account of MySM, you can find like, let's say, more complete example, because today will be a short introduction with silly binaries, just to give you an idea of what you can do with MySM. So please check the blog, they have really cool stuff there. So first, is that big enough? Yeah? Okay. So first, what you can do with MySM is assemble. In order to do that, you need to create a machine, MySM machine. Then you need to get the mnemonic object. So MN object is used to assemble and disassemble. So here you create it. And then you can call the from string function in order to get from this movx1 string into the internal MySM instruction. And then you can call ASM in order to get the binary representation of this instruction. In this case, movx1, we have in x86 32 bits 4 different binary expressions. So I didn't know that before doing this example. Assembling, that's the other way around. So that's a bit Pythonic. Sorry if you don't read Python. So here we iterate over all of the 4 possibilities and just call this in order to assemble these instructions. So I got lucky again. We have the same results when we assemble all of these 4 instructions. Move x1 like 4 times. Next thing we can do, we can play with the intermediate language. So again, here I will start my SM machine. It will be ARM, and I will disassemble 1 instruction. And I don't know what is the meaning of this instruction. So what I can do next is like get his name with .name, it's add, and get this its arguments. In this case, we have 3 arguments. Their type is expression IDs. It's MySM internal expression for registers, so it's R2, R8, and R0. Then we can get another object. It's called intermediate representation architecture. That's a big name and long name, just to say that we'll be able to get the internal representation and later on emulate. So then I can use the getIR function in order to get this kind of long representation of the instruction semantic. Again, it's using internal MySM expression. So what is this add is doing is adding R0 and returning the value, storing the value in R2. Okay, that's one more step towards emulation. So what we can do next is symbolic execution. So first we take this instruction, add it to a block with a add instruction function, and then we can display the current block by iterating over all of the elements. So that's one block. The block starts at address 0. It only has 1 instruction, and this weird stuff, IR destination, that's the internal MySM PC. So we don't really care about that. And here, that's much nicer than the previous representation. R2 is just equal to R8 plus R0. Next step, we can try to emulate that. So first, we get the symbolic execution object. We initiate it, and then we emulate 1 block with a emul IR block. And we can use, for example, dump ID in order to get the modified registers. You can also use dump mem in order to get the list of the memory addresses that were modified. So in this example, this add instruction, at the end, the R2 register will be equal to the initial value of R0 plus the initial value of R8. We can do one more step. Here we can specify a value for R0. Here it will be 0. Emulate again, display the registers, and R2 will be equal to the initial value of R8. And the last step, here I will assign my birthday, so July 28, to R8, emulate, dump the register, and the final value of R0 will be my birthday. Okay. That's nice, but that's a lot of work, like remembering machines and calling instructions, adding them to blocks and so on. So MySM is providing sandboxes in order to do a lot of the work for you. So here I will build a simple and silly example in order to have a binary to emulate. And this silly example will just create an add function that takes 2 integers and return the results. So here I can compile and try it, so it will display 3. That's silly. On the MySM side, what we can do, we can build this sandbox recon.py script. We can start creating a sandbox object. So first, that's mainly boilerplate, when we'll ask MySM to parse arguments, and finally, we'll create sandbox objects. MySM is able to parse ELF and PE files. So I'm using this feature here in order to get the address of add using this line by accessing ELF headers. Then, because it's x86 in 32 bits, I will push arguments on the stack. So it will add these two integers. And this stuff is a bit weird. That's really specific to MySM. I will push the implicit breakpoints, which is the return address of the function. And finally, I will emulate the binary by calling run, and then display the final value. So if I'm doing that, so I'm calling here the Python on the script, and I will specify the binary. MySM will display all of these instructions. So it means that it managed to emulate all of them, and again, will display my birthday. So it's a silly example, just to show you that if you have a function in a binary, you can emulate it really easily with MySM. Okay. There's many more things you can do. Again, you can check their blog. You can attach a GDB to a sandbox. What you can do also, cool feature, you can solve constraints using these three. So you can get the semantics of MySM instructions and then solve constraints. So on this slide, you have like complete examples, again, silly and simple ones, but you can play with them later on. Okay. Then I want to show you how you can implement a new architecture to MySM. So that's exactly what I did for MEP. And to do so, you need to take 3 different steps, and they are not that complicated. Sorry. So the first thing you need to do, you need to specify or, let's say, implement registers in the rex.py file. Indeed, I won't describe that today because it's mainly strings in a file, so it's not really interesting. Then you need to define opcodes in the arch.py file, and finally the semantics in a sem.py. So, arch. In this example, I would want to add an instruction to MySM. It's add immediate in MIPS. So what we can start to do is check the specification of this instruction. And the specification says that first we have 6 bits, 001, 001, then 5 bits that encode the source register, 5 more bits that encode the target registers, and finally the immediate encoded on 16 bits. And in MySM, all you need to do is call the add-up function, give the name of the instruction, and then define something called a bit string. It's indeed a list of Python objects. So the first bit string will be 001, then we'll give him a variable called rs, another one rt, and finally the immediate. And I will define that in the next slide. And because for this specific instruction, the way it is encoded is not the way it is displayed, we can play with the last list in order to invert rt and rs. Okay. You need to define the arguments of this instruction. Again, there will be bit strings, so rs, the source register, will be a bit string of length 5. And here we are telling MySM that it must be decoded with a MIPS 32 gpreg object. And we do the same stuff for the target register and the same stuff for the immediate. And all of these MIPS 32 objects, or whatever, let's say a map object, they need to implement encode and decode in order to return MySM expressions. And MySM will take care of everything, like getting some bits from the binary and calling this method. So that's why I'm saying it's really expressive and it's really easy to add a new architecture. So here's a simplified example of the immediate. It's almost what you will find in the MySM source code. So this object, it has a decode function, and the decode function will take a value from the binary and return a MySM expression. In this case, that's an integer. Encode, that is the other way around. It's taking the internal MySM expression and returning here the value that will be encoded in the binary expression. Okay. Then you can add a new opcode in same.py. So the idea is to implement the logic. So what you can do, the first solution is to go, let's say, the hard way, and you will write full and complete MySM expression. So here it's XEAF to affect, up to specify add, and so on. It's a bit long, and obviously in order to implement add, that's too much. So what you can do instead is be lazy like me and implement the semantics using something they call the same builder. And at the end, what you need to do, and the only things you need to do in order to implement this add instruction is defining a Python function, add, specifying its arguments, indeed the instruction parameters, and just write destination equals source plus immediate. So it's really, really cool and simple. And finally, if you go back to the previous slides, if you remember, we used the getIR function in order to get the internal MySM expression. We can do the same. And here we can see that if the encoded instruction was add A0, A1, 2, we'll have the following MySM expressions. That's really nice. And then MySM is taking care again of everything by using the sandboxes and so on. So demo 2, this one, I need to apologize, is less graphical. So what I want to do in this example, I want to execute a Python sandbox on the MEP target. It's a bit small. Okay. I want to emulate a function that is playing with a network. It's called send login message, and that is a function that will send you back the banner, the telnet banner, when you connect to this specific device I'm trying to reverse. So the goal of this script is to launch the full binary, so it should be 16 megabytes, and go to a specific address, the address of the send login message function, and emulate the function. And this send login message function is doing more calls, for example, to malloc, strlen, printf, and obviously send. And what I did in this Python script, I asked MySM to put breakpoints on these functions in order to emulate them in a different way. So for example, for strlen, I asked MySM to put a breakpoint on strlen. So MySM will stop the sandbox and call a specific callback in Python. The callback in Python will access registers values from Python. For example, in map, it will use r1 in order to get the address of the string, do the length computation with Python, and then set the value of the register with Python again. So what we'll have on the screen when I will press enter, we'll have all of these instructions that are emulated by MySM. In red, you will get all of the functions that are indeed executed in Python. And in green, you will have the final string that is usually sent over the network, but today it's displayed on the screen. Okay, good, it worked. So here on top, okay. So here on top, at the start of the function, there is like some instruction playing with SP. Then here on strlen, we'll see that there is a value. That's a string address, which is set into R1, and then MySM will break on strlen, emulate it, compute the string length, store it in R0, and follow the execution. So it's doing that for strlen several times. Calling malloc, again, that's a weird trick to emulate malloc in Python. Calls sprintf in order to build the final string. And finally here, instead of sending to the network, we will just display the banner. Okay, so it's a really silly example, but as I said before, my main job is to do network. So from time to time, I'm reversing network protocols. So here the use case could be, let's say you have a weird network protocol, you reverse it, and you implement it in Scapy, of course, and then you want to play with it. So what you can do, you can emulate the banner in MySM, check that your implementation is complete, and once it's complete, you can send the packet to a real target. So I think this demo is short and not visual, but can give you some idea of what you can do with MySM. Okay, next thing. So it took me, let's say, 6 months to implement the architecture in MySM. Not because it was difficult, because I had no time to do it. And at the end, I could only emulate the binary, assemble the assembler, so it was not better than objdump. So I played with internal MySM tools, for example, the full.py script. Full.py, you give him a binary, he will disassemble it and give you a dot file. So it's exactly the same graph format as the one that was discussed during the first talk. And at the end, you can get something like that, which is a call graph. So it's the same output as the one I showed you in R2 during the first demo. So it's the first jump from address 0 to address 100. So it's nice. You have a call graph comparing to objdump, it's better, but still it's too difficult to do some real job done. So what I did next, I decided to have a look at R2 plugins, and mainly R2 plugins in Python. So the goal here again is to call Python from C. First thing you can do, and that's really simple, you can use R2PM. R2PM, that's a R2 package manager, and you can use the lang Python binding, and that's it, if you want to write a plugin. You have on the r2m2 source code, you have this example. So if you want to write a first radar plugin, you need to implement assembly function. The assembly function will take a string, movx1. In this case, you will use a MySM machine and return the bytes of this instruction. You can also define a disassemble function. Disassemble function will take a buffer. We'll again use a MySM machine, disassemble one instruction, return its length, and it's a string like jump, address something. Then what you need to do, you need to define a specific Python dictionary with such things as name, arc, bits, and so on, license. And indeed, that's the exact same names as the C elements of the structure used by R2. And that's it. And then you need to initialize your plugin. Finally, if you go to a shell, you can type R2 -i, the name of your Python script, which is now an R2 plugin. You can initialize the architecture. You can give him a binary, in this example that ls, and disassemble 5 instructions. That's nice. And you can also use PA to assemble a knob. So it works. However, there is an issue because today there is only assembly and disassembly plugins that can be implemented. So it means that at the end, you only get something just a little bit nicer than objdump. There is no way you can get the call graphs. There is no way you can get the instruction semantics by implementing this assembly and disassembly plugin. So in order to implement the other plugins called AE for analysis and Ether, that's the R2 expression names, I needed to do something else, and I'm not really proud of that, but the idea was to call Python from C. So in order to call Python from C, the best solution is to use the CFFI Python module, because at the end, it will take your Python script, put it in a dynamic library along with the Python interpreter. So what I want to show you next is how you can do that. So again, silly example, what I want to do is to call base64 from Python. So first, you need to define an include file with a base64 function. That function will be exported in the dynamic library and called from C. And finally, you need, again, silly example, that will call the base64 function. So in C, that's nice, and C doesn't know that indeed the base64 function will start a Python interpreter and call a Python function. In Python, you need to define a new your specific Python script, so that's what I'm doing for r2m2. First, you need to start the object and then tell the CFFI Python library which function will be exported. So here that's simple, I'm just opening the include file and giving the embedding API function the content of the include file. And then you need to define what to do. So here again, that's simple. I will create a base64 function in Python. First, I will convert a C string into a Python one. Then I will print the value, and finally use encode base64 in Python in order to retrieve the base64 value and return a C object or a C value. Okay, so next you can compile. So first you call Python in order to get the dynamic library, and you can compile the binary. Then you can enjoy and test it. So here we have a string and the base 64 corresponding value that was computed during using Python. That's a bit silly, but that's one more step towards calling MySM from C and calling MySM from R2. Next thing I did was to try to access R2 structs from Python. Indeed, it was not the best choice because there is many limitations. The first one being that the CFFIC parser does not support all of the C extensions. So from time to time, you won't be able to parse or include files, and you won't be able to call to get the R2 structures from your software. So at the end, I played with many different possibilities. You can check the links here. They are interesting, but not for this talk. So what I did, I chose to extract R2 plugins myself using a really simple Python script in order to remove these limitations. Okay. And the third step you need to take, you need to build a R2 plugin in C. You can check the wiki, R2 wiki, because they have a really nice example on this link. And I won't describe that today because that's, I guess, too much information. And that's exactly the same as we did in Python like 5 minutes ago, but in C. So you need to define disassemble function, assemble function, and you need to fill a C structure. And that's it. You get a R2 plugin in C. Okay. So at last, R2m2. R2m2 uses everything I described so far to bring MySM to R2. Again, it keeps most of the smart bits into MySM. And at the end, it provides two plugins. The first one is called AD for assembly and disassembly. So that's same stuff you can do in pure Python. But the most important part, that's AE plugin, analysis and Hazel. If you have R2m2 installed on your laptop, device, computer, you can call RSM-L and check that R2m2 is actually providing AD-AE features. Now I want to briefly discuss what I did in R2m2. So R2m2 AD, that's the easy one. It's just basically a CFFIC wrapper around the MySM machine. You can use it this way, like in the demo. You can export the variable, and you will specify the interface. You can use, for example, RSM2 in order to assemble one instruction and store it in a binary, and then you can disassemble the instruction. Okay, and everything is done with MySM. So again, that's R2 calling Python, calling MySM. Okay. Here, that's the output on binls. So again, that's nice, but it's not better than objdump. Why? Because here you have jumps here and there, and we don't know where they go, and R2 is not able, for example, to build a call graph. So it's not better than objdump. Okay. So the challenging plugin was indeed R2m2 AE, because MySM was, I needed MySM to find branches, function calls, blocks, and emulate instructions. Indeed, that's not that difficult. In R2, for all of this, all of the instructions like move, jump, call, R2 will assign types. For example, if you have a move, it will say, okay, the type is R2 move, same for jumps and so on. So the first type I did in R2m2 was to assign R2 types based on some MySM functions. So here, that's an example. We have in Python an instruction, MySM instruction. I will call a subcall. So in this case, MySM is telling me that this instruction is a call. Then I will check the first argument type. If it's an integer, then I will set the type of the instruction to be a call, and I will try to compute the address. Of course, depending on the architecture, this could be incorrect. Otherwise, if the type is not an integer, I will just say, okay, that's a call, but that's an unknown call because we don't know where it goes. Okay. The most interested, okay, no, let's take the example. So here I will assemble a jump nop, which is a bit silly, but I just want to show you that, compared to what I showed you before, in this case, R2m2 is able to decide and know where the jump is going. It's like just pointing at the knob, but again, that's one of my silly examples. Okay, and the last thing I'm doing with R2m2 is to convert MySM expression on the fly. And the interesting part here, like both MySM expression and Hazel, they try to achieve the same thing, which is expressing instruction semantics. And indeed, automatic conversion are possible. So on top here, we have a M2 expression, here a R2 expression, and that's what r2m2 is doing, like converting them. And there is one more step r2m2 is doing, is providing the definition of registers on the fly by reading the rex.py file and specifying that to R2 using a R2 API. Okay. So what we have next, we can use R2 on the same binary, jump nop. We have again that here that says that the jump here, this instruction will go to the nop, and the main difference is here R2 is aware of the instruction semantics. So after the jump is executed, the PC value will be changed. So that's exactly the same I showed you during the first demo. Okay. Third demo, so it's like putting everything together. So I need to go back to R2. Oops. Okay. So first here I will load some function definition of R2. So AFL will list a known function. Send login message, that's the function I showed you before, the one which was emulated. So I can jump to the address, analyze, oops, and get the call graph. And what I want to show here, for example, for this move, okay, oops. For this move, R2 is able to know, because of the semantics and expression conversion, is able to know the address of R1 and is able to tell us that at this address we have a string. And also because I told him that this address is the address of strlen, it will display this nice stuff. So by using dynamic features of MySM, I was able to enhance, thanks to R2 features, the display I was getting from this map binary. Okay. And I think that's it. So roadmap, r2m2 is still under development. It works fine for my usage. Hopefully it will work for you. And something I would like to do, I would like to define a calling convention dynamically. And my main goal here is to enhance again the display I can get in R2. A month ago I was on my way back from CCC and I couldn't get in the plane. So I went from Hamburg to Paris by train. So I had a lot of, like, let's say 7 hours to spare. So I did a POC in order to implement calling conventions. So here on the display, what you can see, that's this time for strlen. I hope it's not too small. R2 is able to tell us that the strlen function will be called on this string. So again, that's something useful in order to help me reversing the binary. Okay. To conclude, first I would like to thank the MySM and Radar people. So it will be François. I would like to thank François, Camille, and Fabrice, and also from the Radar community, I would like to thank Pancake that will help me a lot on the r2m2 plugin. So they are both powerful tools, and it turned out that combining them was really efficient for my use case. Yeah, last thing, like r2m2 is more than a proof of concept that only works on my laptop. You can get it on GitHub. You can run it with Docker. And one open question, like, is it too good to be true? That's an open question from me to you, because I said before, I don't reverse for a living, so maybe my assumptions are like too simple, and this r2m2 plugin won't be able to work on a bigger use case. So thanks a lot. Thanks for the REcon organizer. If you have questions, comments, beers, I will be here until tomorrow, so let me know.